part of the solid is I'm going to erase this, is 2 times the double integral, I'm going to polar, r d theta. That has to be this order because theta is between 2 constants. They were negative pi over 2 and pi over 2. My radius was stuck between 0 and 2 cosine theta. And then it was just the f function minus the g function. Here's the f function. But to polar, what is that in polar? Root 9 minus r squared, right? Minus 0, so it doesn't matter. And that's it right there. And then you would go and integrate that. But I'm not going to say dot, dot, dot here. This we could not do by hand. The first integration is easy. The first integration is a basic u sub. But the second integration, I believe you would wind up getting something like you're trying to integrate, forget about constants, but I believe it's something like square root of like 9 minus 4 cosine squared, if I remember correctly, something like that, d theta. Something like that. You're trying to integrate that. And that ain't happening. So that's why I changed the problem on the take-home. Questions? Your problem that is on your take-home exam is very similar to this problem. In fact, I probably gave you way too much here. But your surface on top and bottom is a little different, and it makes the integration possible. It's going to be a little messy with the integration, but all within, fair game stuff. All right, so what would we do now to find the final answer? If we were able to find this volume, right? We got it. We double it here already, right? Find that answer. We take that answer and subtract it from the volume of a sphere, which you have to go figure out. The difference on your take-home problem is since it's not a sphere, right? You don't have a formula for it, and therefore you have 2 problems that you have to do here. You have to find the volume of the paraboloid first, which is a double integral. Then you come and take this away. Do you understand how that's 2 different problems? Okay. Enjoy. All right, that's it for that section. We are going to very briefly talk about 12.4. And when I say brief, I mean we're going to be done here in 20 minutes, I think. So some of the applications. We can get really, really heavy into applications in this class, or we can actually finish the book. And I choose to finish the book as opposed to do heavy applications, only because everything we've done so far is enough for you to do this. It's just a matter of making the connections between, a physics class and a double integral in there, and then doing the double integral, which is what we're trying to show you here. But here are some of the things you can do with double integrals. Suppose you have a lamina. A lamina is like a 2-dimensional sheet, a piece of paper. That's a lamina. All right? And it has some weird shape to it. Here it is. And then the density at every point, right? Remember, density is mass divided by area in this case, because it's 2-dimensional. So you're looking at, what you're trying to do is you're trying to figure out what the density is at each point, and then you can ask questions like, well, what's the mass of this thing? Okay, what is its mass? So what we deal with in terms of laminas are what are called homogeneous laminas, which are laminas like a sheet of paper, where we assume basically the density is always the same. You know, if you cut out a 1 inch by 1 inch square from anywhere here, take two of them, two 1 inch by 1 inch squares, and weigh them, they should weigh about the same, right? Because we're assuming the density of the paper is the same throughout, uniform, homogeneous. And then you have laminas that are non-homogeneous, which would be something where the density varies throughout the lamina. And that's what we're interested in. What if you have a more complicated lamina where as you look through it, its density changes? So suppose the density is variable, all right? Then the total mass of the lamina is the sum of the mass at infinitely many infinitesimal rectangles. So you're basically cutting up this lamina into a bunch of little tiny rectangles, and you're finding the mass at each one. And if density, if you know the density at every point, so that has to be given to you, the density at every point, density being mass over area means that you can solve this for mass, and mass would be equal to density times area. Density you're given is a function. Here's your density function. So density you're given, area we know, because that's what we've been doing. So you're adding up all these little masses, which means you add up the density times the area. And that's, replace that with F, and that's what we've been doing, right? So all that's changing here is that we have, the function actually means something now. F of xy, if it represents a density function of a lamina, then doing that double integral over that region gives you the mass of the object, mass of the lamina. If instead we like to do, you know, something that involves electromagnetism, something like that, we could look at a lamina again, a flat sheet of paper, and we could say, hey, look, check out this sheet, whatever it is. It has a charge at each point. Some charge density is what they call it. Then if you look at and you're trying to find the total charge on this lamina, then what you do is you multiply the charge density times the area, and you get the charge at each little infinitesimal, and you add those up, you get the total charge. So again, it's the same concept. What is the meaning of this function? In the previous example, rho of xy was a density function. In the second example, it was the charge density. So if you do this double integral, it gives you the total charge. Again, all I'm trying to do is trying to get you to see that in a physics class, if we give that function f, which is what we do in this class, f, if we give that some meaning, then we can correspond it to either like total charge or total mass. And there's no restriction. It doesn't have to be just those two functions, but those are common ones. So a lamina is formed by the region bounded by these curves. The density is given by this density function. Find the total mass. So this one's going to go fast. I have a lamina 1 minus x is that. Y equals 1, x equals 1. So y equals 1 looks like this. X equals 1 looks like this. Everybody see the region bounded by those three? Okay. The density at a point in that lamina is x times y. So if I come out here and I say, I don't know, I pick the point 3/4, 3/4. That point lives in there, doesn't it? What's the density at that point? What's the density of the lamina at that point? It's the x times the y, right? X times y. So it's 9/16, whatever they're measuring it in, right? But if I change and I move this to 1/2 and go up 3/4, then now it's changed, right? Now it's 3/8, different density. So this lamina, its density changes throughout the shape, throughout the figure. And we're trying to find its total mass. So all it would be is what? Let's see how many of you got this down. See a lot of glazed staring into nowhere. So how do you want to do this? Do you want to go polar? Every time I say, do you want to go polar, I always think of, do you want to go postal? You've heard that before? Postal, like go crazy? Isn't that a term that they use for that? Go nuts? How do you want to do this? Type 1? Type 1 region? Okay, I agree. We're integrating. What are we integrating? What's our function? XY. Since it's type 1, my x's are bounded between two constants. What are they? 0, 1, right? 0 to 1. My y's are bounded between two functions of x. This one's the bottom one. This one's the top one. So the bottom one is 1 minus x. The top one is 1 d y dx. If you can compute that, you've got the mass of the lamina. All right? I'm not going to. Questions? This is the same exact problem. Everything's the same, except instead of using a density function, using a charge density. So the only difference is the answer means something different, right? If you find this integral, that answer would represent the total charge on that lamina. Now, along with being able to find the mass of a lamina, you can find what's called its moment. Now, this is a physics concept. And we use the moment to compute something else. So first, let's talk about what the moment is. Same lamina, right? There it is. Blah, blah, blah. It's got a variable density. So we still have the charge density, or sorry, the density function right here. You see it? But we've added one thing to it. You see the y right there? Y times the density function. If we compute this, it's called the moment of the lamina about the x-axis. And we use capital M subscript x to represent the moment of the lamina around the x-axis, or about the x-axis. If we switch it, and instead of multiplying by y, we multiply by x, we call that the moment of the lamina about the y-axis. So physics again, moments are basically the mass of the particle times the distance to an axis. Now, why is that useful, computing the moment of a lamina? Well, the next one.